Test. Perfect. Sorry about that, everybody. I was having a little bit of technical difficulties logging in, but I'll get started right away. I'll make sure to make up for the time. My PowerPoint isn't popping out. Go. Hello, hope you can see the screen okay now. Okay, thank you for coming to this concept live stream. My name is Ian, and today we're going over Map 117. Specifically, we're going to be looking at graphs of logarithmic functions. Or if you want to see a PDF of the problems I'll be working on today, feel free to go to this link, and you'll be able to find them. Thank you for tuning in. This session is being recorded, so please be aware of that. When it's done being recorded, it will be sent out to you guys, and you'll be able to rewind as much as you like. So please behave while you're in chat. With that being said, let's get started with this first problem I have here. So with this one, we're kind of looking at what a logarithm is. It's telling us to graph y equals log x, then rearrange the function to show what exponential function the logarithmic function is equal to. So if we look at the equation, y equals log of x, what does this mean? What is log x? Because typically when you see a logarithm, it has a base, and then you have the number you're working on. So with log x, what is our base? Feel free to try and shout it out in chat. Oh, sorry. So when you see an equation that just uses log x, that's the same as writing log base 10 of x. And if we were to look at the equation of this, if we try to plug in log of 0, we're going to find that we don't get anything back. And when we look at the graph, and then if we plug in a 1, we're going to get 0 back. So if we look at the graph, here's 1, that's going to be where we cross the x-intercept. And we're not going to have a y-intercept. It's just going to keep decreasing forever, but never reaching 0. And so if we wanted to graph something equivalent to this, we would need to look at this function in an exponential form. So if we did that, if we changed log of x into y, we're going to use the base. So if we rewrite this using properties of logarithms of exponents, we can write it as e to the log 10 x equals e to the y. Or not e, 10, because we have a base 10. So then we can write it that x equals 10 to the y. So if we were to plot that, you'd get a graph that looks like this. Because if we flip it over, we have an x and a y. And then as the y increases, the x increases. And as the y decreases, the x gets closer to 0, which is just like the exponential function. So that's just one thing to keep in mind in how logarithms can relate back to exponents and exponential functions. So moving on to the second one, we can try and compare the graphs of f of x, f of x equals log base 20 of x, and g of x equals ln of x. So let's write them down and compare them side by side before we look at their graphs. So when we look at f of x, right away we can tell that the base is 20. So if we were to write that in exponential form, it would be 20 to the y equals x. And with this one, we see it's ln of x, not log. So what is this one then? What's ln mean? How can we write it as log of x? Well, the natural log of x, this means we're using a base e. So if we see this, it's the same as this down here. Just one thing to keep in mind. So if we want to rewrite that, we could write it as e to the y equals x. So if we were to graph f of x, it's going to look similar. You're going there, and we cross at x equals 1. And then if we do natural log of x, it's going to be pretty similar in the beginning. Except you'll notice that the natural log of x goes up higher. I guess a better way to draw this would be, let me do this one in red, and say that that's f of x, and that in a different color, in blue, that's the g of x. And so how can we tell that it makes sense that g of x seems to be increasing faster than the f of x? Well, if we look at these and we kind of flip the equation over on its head like we did on the last one, we can kind of make sense of things. Over here we had y and x, here we'll have x and y. So for f of x, as the y gets bigger, the x gets bigger, right? And notice that y is getting bigger pretty slow, but x is getting big really fast. It's sticking close to the x-axis. And then for g of x, again, as y increases, x increases. But now the y increases and the x doesn't increase quite as fast. Because now our base of the exponent is smaller. So we can say that it's decreasing faster. So when we flip it, the one that's increasing faster as an exponent is increasing slower as a logarithm. And then the one with the smaller base that's increasing slower over here is increasing faster over here, if that makes sense. So we can kind of see like where the relationship comes from in the log form. compared to the exponential form. So let me move on to the third one. So now we're looking at more graphs, and we're going to see how different translations, reflections affect graphs of logarithms. So with A, we have a negative sign. So we're going to reflect it. So if I start by drawing ln of x, we can see the change more obviously. So I have my ln x in red, and I'll draw my f of x in blue. So if we have a negative sign, what does that do to a function? It's going to reflect it over the y-axis. So now, if we were to plug in ln of 0.1, instead of getting something that's really close to 0, we're going to get the opposite. Or we're going to get we would get something close to 0. When we have a logarithm and we plug in something getting closer to 0, say natural log of 0.001, we get a small negative number because we're getting closer to a negative infinity. Sorry about my words earlier. So when we flip it, now we're actually getting closer to infinity. And instead of increasing forever, we're actually decreasing. Because then if we tried plugging in a really big number, say something like 10,000, we would get 9.21. And when we flip it, we get a negative number. Sorry about that. And it'd cross over at 0, 1 because, or at 1, 0, because when we plugged in 1, we'd still get because an ln1 would still get us a 0, and flipping that would keep it at 0. So yeah, when we reflect it with the negative sign, we just reflect it over the y-axis. So let me move on to the next one. All right. So now we have g of x equals ln x plus 5 minus 1. So I'm going to start by drawing in ln of x in black. And that's the one we've been used to seeing now. It crosses at 1, 0. Then, what will adding 5 on the inside do to the function? Are we rotating, reflecting, or translating? So if we put in a +5, we're going to translate the function, and a +5 means we're going to the left 5 units. So now, instead of it happening at 1, at -4, I mean, yeah, sorry, yeah, at -4 is where we would cross. So let me put a different color, sorry. And here at -4 comma 0 is where we cross the x-axis. When we translate 5 to the right, so we're going to the left 5 units. So then, once we do that, we can look at the next part. I'll put it in a different color, a -1. How is this one going to affect the function? So when we have the -1, that also translates. So now we're going down 1. So this -4 is comma 0. I'm going to erase this. Don't worry, this will be recorded. It'll be a little rewind. We'll go down 1 unit to -4 comma -1. And we redraw our function like that. So then that's how g of x will look when we sketch it. So when I try and do these sketches, try and keep myself from getting like confused, because I know when I look at graphs I get a little tensed up. I just try and take it one step at a time with the translations. So now we have C. We have negative the natural log of x -1 -4. All right. So let me clear off the screen. So if we start to draw a sketch, let me start by drawing natural log of x. That looks bad. Maybe something like that. Again at 0, 1. So if we reflect that with the negative sign, and have one going down like this, then we have a -1. So whatever's happening to our function, we're shifting it. And so for a minus, are we going left or right with this translation? Yeah, so with the minus sign, we're going right 1 unit. So now this 0, 1, not 0, 1. 1 comma, wrong color. Sorry about that. 1 comma 0. Then in blue, going that way. To yellow, we have, we're shifting 1 unit this way. So now we're at 2 comma 0. Hope that's okay to see. Oh, sorry. Then with another color, we have a -4. And the -4 is going to translate us. We're going down 4 units. So then we can move this point down 4. And we're at 0, so down to -4. And then we can bring the rest of the graph down too. Sorry about that. We're at 2 comma -4. So then in green, well, I didn't really label these, but so in green we have our final function that we want. And then using various colors, I showed how the reflections lead to each other. So in yellow we have negative ln x minus 1. In red we have the base ln x. In blue we show how the negative affects it. And then finally in green we have our final function, or our original function that we want to show the sketch of. All right. So if we want to see, so there's an example of sketching. If we want to see how we can use a logarithm to solve a problem, for example, let's say that we have a function that's the negative logarithm of x plus 2 minus 1, and we want to know when f of x equals, let's say 10. We'll say -3. How would we do this? Well, like any other function, you'd start by writing down what you need. F of x equals -3. So we want f of x to be -3. So we set our function equal to -3. And from here, it's all about isolating that x. So we can add 1 to the other side. Oh, sorry. So we can add 1 to the other side. And then we can bring down what's left. Then to isolate the x, you want to get rid of any coefficients with the logarithm. We can say that 2 equals natural log of x plus 2. And to get rid of a natural log, we need to use an exponent. The same way, plus and minus are related, and then multiplication and division are related. We can use logs and exponents. So in this case, we have a natural log, so we might want to use a natural exponent. So if I write over here, if we raise both sides, we can get rid of the natural log and get the x by itself. So now that we're here, we can say that e to the 2 equals x plus 2, because whatever's in the parentheses are bringing out, and e to the ln of. And then e to the ln with nothing is just 0. I mean, it's just 1. Yeah, e to the ln1 is just 1 once we bring out the x plus 2. So now that we're there, we can solve for x more easily because now we don't have a natural log in the way, and say that x equals e to the 2 minus 2. So that's an example of how we can use natural logarithms and logarithms in general, trying to solve a problem involving them. And knowing how the function looks like can help us just to know in general what the answer should be. So if we have e squared minus 2, I think e is about 2 let me see, 2.72 minus 2, so that's about 0.72. At 0.72, we're at a -3. So if we looked at the graph of this function, we can try and sketch it real quick and see if that answer makes sense. So if I do that, we know we see a negative sign right here. And just like before, we know it's going to reflect it. So we're going to start, if we started with a regular natural log, we would have been here. But when we reflect it, now we're reflecting across the y-axis, so we look like this. Then this plus 2, that's going to translate, right? And it's a plus 2, so when it's inside of parentheses, we know a plus actually means to the left. So we can move our function 2 units to the left. So now this is our function. Whoa. And if we moved it 2 units to the left, it was crossing at 1, 0. So now we're crossing at -1, 0. And then we finally have this -1. And that also translates. And since this is outside, the negative means we go down. So we're shifting this one down, 1, 2, -1, -1. And we're going to shift the whole function along with it. Just pretend I made it. So we can get rid of this. Now if you look at when it's equal to -3, it's over here on the positive side. Oh, sorry about that. Which is what we got, just before 1. So our answer looks like it makes sense when we look at the graph. Okay, that's just about all the time I had for this session. Let me look at the problems real quick. This recording will be sent out, so you'll be able to go back. Excuse me. Once you get the recording, if you want to get more tutoring, go to this link right here, bit.ly/10p tutoring. That'll take you to our Zoom room where we have tutors online ready to help you with your homework or other questions you have. And then we have these 30-minute concept live streams on Tuesdays and Thursdays. So feel free to tune into those. Then on the Zoom Tutoring Center, Tuesday nights and Wednesday mornings are math nights. So there'll be like a lot of math tutors. So that might be a good time to go in for a question. So that's all I have for today. Hopefully I'll see you Thursday for the next session we do. Thank you for coming. I hope this helped, and I hope the recording will help out in the future as well.